Hello everyone. In this lab, we are going to learn about line models in ANSYS. Here you can see the contents of the lab. I'll show you the general overview of 1D line elements, and then we will model a flexible gripper in ANSYS and analyze it for stresses and strains. Then we will model a tower crane and we will analyze it for stresses and strains. And finally, there is this one assignment. So why we use line elements? Some of the real world problems, they can be solved using these, and it reduces the computation time in large problems. Apart from that, it also simplifies the problem. So let's consider a simple 2D box. Here's a question for you. Can we model this box using the line element? And the one thing that we need to take care of is the lines, they do not have any width. They only have length. So to answer this question, we need to dig a bit into how FEA works. Let's look at the example of the spring element. Here you see while solving for spring element, we write the equation for each of the spring element in terms of F equal to Kx, where K is the stiffness matrix. And in general, the K matrix, it has the properties associated with real world objects. Like in case of springs, this K is the stiffness of the spring, and in case of truss, it could be area or maybe moment of inertia. So when we look at the truss element, this is a truss and there is a force F that is acting on the right side. And if this truss moves by the distance x, we can write the deflection in terms of F equal to Kx. Here you see this is the formula for deflection, where the force can be written in terms of F equal to A, which is the area of this truss, cross-sectional area, E is the Young's modulus, L is the length, and X is the displacement. Since A, E, and L, they are the properties of the cross-section and material, we can combine these in single constant K. So it can be written as like this, K equal to AE by L. So we can model this truss as line elements like springs, where K is defined in terms of area, E, and L. However, in this case, the element, which is the line element, it cannot have sub-elements in other two directions, which can be y and z direction. So y and z direction, they are specified as properties of the line element, where it has all the information related to the area, elastic modulus, and length. So in case of beam elements, you can see that the K can be written in like EI by L cube, and this matrix is based on length of the beam, and I is the property that depends on other dimensions of the beam. So if we specify the moment of inertia for line element, we can model a beam using a line element, which will have all the information related to the actual beam. So in summary, yeah, line elements can be used if we specify the properties based on other dimensions. And we have the length, which represents the size in one direction of the geometry, and then we have the cross-sectional properties that we specify using the type of the cross-section and its dimensions. So let's look at an example. Here is an example of a flexible gripper. It is made of polyoxymethylene, and its Young's modulus is 2 gigapascal, whereas its Poisson's ratio is 0.35. So the objective is to find the total displacement of point P4 if P7 is moved 1 millimeter in negative y direction, here negative y direction based on this coordinate system, and we need to find the maximum stress in the gripper. The cross-sectional area of the gripper is 1 by 5 millimeters. So there are two ways in which we can model line elements in ANSYS. I'm going to show you both one by one for this flexible gripper and the second one for this tower crane. So let's move on to ANSYS and see how we can model this gripper in ANSYS using line elements. The first step in ANSYS is to add the engineering data for the material that we are going to use before modeling the geometry. So the material is polyoxymethylene, so I'll use it POX here and add the isotropic elasticity where the Young's modulus is 2 gigapascal to E9 and the Poisson's ratio is 0.35. After adding the material properties, let's move on to next step, which is modeling the geometry. And for line elements, the analysis type needs to be set to 3D. So you see that ANSYS only have two different analysis types, 3D and 2D. Although in line element we only model the length, however that length or particular shape of the line can be oriented in 3D space. So ANSYS allows us to model a three-dimensional object like a bike, maybe frame bike or chassis, using line elements that are placed in a 3D space. So that's why we are using the analysis type 3D. So I'll just open the design modular. After opening the design modular, let's change the units from meters to millimeters and go to XY plane where we will start our sketching. So in order to sketch, we need to add the construction points, which are like 7 points in XY plane. So 1, 2, 3, 4, 5, 6, and these are 7 points. First of all, I'll dimension these points from X and Y axis. So this first dimension is 70 millimeter on x-axis. Then we have this second dimension, which is 90 millimeters. Next is 69 and then 35. So this is 69 millimeter. Then we have another point at 30 millimeter. So it's 35 millimeter in x direction. Let's change the dimension of other points. They are 34, 24 and 0. So this is 34, this is 24, and final point is on y-axis already. So now we need to add the y dimensions of all of these points. Starting from this 0, 40, 120. So this is already at 0. This point is at 40. This next point is at 120. Finally, this point is at 160 millimeters. Now we have the remaining points that are at 100, 60 and 50. This is placed at 100. The next point is placed at 60. So this is the one. And final point is placed at 50 millimeter from the bottom. So here we have 7 points that define the basic structure of the gripper. So I'm going to model one half portion only, and in order to do so I'll use this spline. The spline will start, so there are two splines. The first one starts from this horizontal axis going to point 2, then this point, then this point. After clicking on these points, I'll use the right mouse button so that I can see what are the options that are available in order to have this spline. So I'm using this open end option. So this is a good looking spline for the gripper. Now similarly, I have another spline starting from these points going to this point, and this is also the open-ended spline. This way I'll have this basic sketch of the gripper, and I can convert this sketch into line bodies. So in order to do so, I can use lines from sketches option here, and here this is the sketch. I'm going to select generate. So you see that a line body is generated here by ANSYS using the sketch that we have. It appears under this line body. However, whenever we add these line bodies, we need to add the cross section of each line body so that we will have the properties of the cross section in the stiffness matrix as I discussed previously while defining or discussing the details about line elements. So in order to add the cross section, ANSYS already have some built-in cross sections, so we can use these built-in cross sections or we can use this user-defined cross section. So in our case we have a rectangular cross section and its dimensions are 1 millimeter by 5 millimeter. So I'm going to set this to 1 millimeter and this is 5 millimeter. Now I can assign this cross section that I defined there at the top, and after defining this cross section we have this body here. However, for now we cannot see how this cross section is looking. In order to look at the details, I can go to this view option, and here we can select this cross section solids. So we have the cross section that will look like this. So this is a line body with cross sections. So there is one thing that we need to make sure while modeling the line elements, that the cross section of the line element, it must be oriented correctly. So here by default this is correctly assigned, that we have this small length of the rectangle in y direction, and you can see the height or base which is the larger length in z direction. However, it is possible that this orientation is not correct, and there are times when we need to correct this orientation. For that, we need to go to this edge selection filter and select the line. Here, when you will select the line, we can change the orientation of this section to maybe 90 degree. You see here this cross section is oriented now 90 degree in the direction, or it could be any other angle. So in this case, this is 0 degrees and it is correct. One last thing about the line elements related to geometry is we cannot use the symmetry boundary condition here in the geometry for line elements. So we need to add some alternatives so that we have this symmetry in the model. So for that, there are a combination of two boundary conditions. The first one is the rotate the first one is the rotation at the point where we want to specify the symmetry, and the second one is the displacement. So in order for part to be symmetric, out of plane rotations are restricted, and in plane so I'll say that if this part is symmetric about y-z axis, so the deformation or deflection, I'll say, in the direction in x direction will be restricted here. So we will have the combination of these two boundary conditions will give us the scenario that is similar to the symmetry boundary condition. So here we can close this geometry and move on to the model. So after opening the model, we can assign the material that we defined, which is POX. And you see here the cross sections, they automatically appear for this body in the model from the geometry tab. So the next step is to generate the mesh, and you will see when we create this mesh, the mesh is generated along the line, and it does not have any distribution in y direction. So one line element here. So this one rectangle, it represents a single line element. So this body is modeled as multiple line elements that are connected. And we can fine control these using the sizing. And the sizing, we can select the geometry using the edge selection filters and add the number of divisions. So for line elements, it's very easy to control the number of division. Let's make these to 10 here. So when we look at the mesh here, we have 10 division. We can further refine this to 20 division as well. So these are the 20 divisions. There are 40 elements, 10 for one supply, 20 for one supply and 20 for other supply with 81 nodes. Now let's move on to adding the boundary condition. The first boundary condition that we want to add is to replace the symmetry boundary condition. So for that, we need to restrict the rotation of the body of this gripper at this edge. So I'm going to select this vertex filter, select the vertex where I want to restrict the motion, and I want to restrict the rotation in y direction and z direction. In x direction, this is free. So this is the first condition. The second condition is the displacement one at the same edge. Here the displacement in x direction is set to fixed or 0, and as a boundary condition, we are changing the direction of this point P7 by 1 millimeter. So we are moving this 1 millimeter in negative y direction, and displacement in z direction is free. The second boundary condition is at the other edge, which is the fixed boundary condition, fixed support at the other edge here. And in the solution, we are required to find the total displacement and stresses in the gripper. So I will insert here. You see that when we are using the line elements, we have limited options where we can view the result. So one new option that you can see here, they are the beam results. So we can see the bending moment diagrams and shear force diagrams here for the line elements, and there is this beam tool which tells us about the direct stress, combined stress, minimum and maximum, and the maximum deformation that we want to find. So I will just run the solution here. So the total deformation in the body is 1.61 millimeter, and if we want to find the deformation of point number 4, which is at the top, I can insert the total deformation here and go to the edge, or sorry, go to the vertex filter and select the point where I want to see the deformation and evaluate the result. So the maximum deformation at the point number 4 is 1.6 millimeter. When this point number 7, it moves 1 millimeter downward in the direction. Finally, if I look at analysis setting here, one option under solver control is large deflection. So in ANSYS, there are three kind of non-linearities that can be modeled. The first one is the material nonlinearity, where we can use a material where the elastic curve is not linear, or maybe we want to see the behavior under plastic deformation. For that, we can add the nonlinear curve for stress and strain and analyze the structure for that material properties. The second type of nonlinearity is the change in the contact status that we have discussed in the previous lab, where the frictional and rough supports can be modeled and the contact status can be changed during the simulation. And finally, we have the geometric nonlinearity, which is related to the change in shape of the cross section if the deflection is very large. And in that case, the stiffness matrix, which depends on the cross section, it will also change while we are solving for the deflections and the stresses using FEM. So to incorporate the geometric nonlinearity, ANSYS provides us with this option, that is large deflection, and we can turn this option on for the analysis. And I will show you the difference between linear and nonlinear analysis here. Let's say that we are moving this gripper by minus 50 millimeter, and in the analysis setting, non-linear controls or large deflection control is set to off here, and I will solve this and keep a note of the result for the total deformation. So in this case, the total deformation is 80.73 millimeters. So if the input is 50 millimeter, the output is 80.7 millimeter. Let's change the analysis setting and turn on the large deflection option so that we can consider the changes in the geometry. And while doing so, we have another option which is the auto time stepping, and we can change this to either on, which is so in this case, ANSYS will divide this 50 millimeter deflection automatically using the program, or we can use this, we can turn off this auto time stepping and use the number of sub steps for solve for the solution. So let's say we are using 10 sub steps. So how the answers will solve this problem with large deflection on with 10 sub steps? So what it will do is it will divide this displacement into 10 parts. Let's say since we have 10 substeps, so one part will be equal to minus 5 millimeter in this case. So it will solve the problem for minus 5 millimeter and then calculate the deformation and change in the area using the Poisson's ratio, and after calculating the new area it will add further 5 millimeter displacement to the problem, so the net displacement will be 10 millimeter, and will use the updated area that was calculated in the previous substep for further solution, and it will repeat this process 10 times for each substep. So if we incorporate these nonlinear controls, the solution time will be a bit larger for very complex problems. Here you will see there is a very little difference. However, the results, if we look at the results, in this case, the maximum deflection in case of nonlinear controls, it goes to 77.8 millimeters. So 77.1 millimeter, and this is how the answers solved this in 10 different steps here. So these are 10 different time steps, sub steps, and for each sub step we have the deflection 8 millimeter and then changing to 77 millimeter. So by turning on the large deflection, we incorporated the non-linearity that was related to change in geometry because of the extreme loading conditions. So I will move on with the second method of modeling, which will be related to this tower crane. So you see, when we have very large number of data points, what we can do is uh, I'll just add another structural analysis here. So when we have very large number of data points, we can, instead of directly adding those data points one by one in ANSYS, that is time consuming, we can create a notepad file, or you can, or a CSV file using Excel. So I'll use this notepad file here and add the data points that we have for all of these joints. So the notepad file, it consists of 5 different columns. The first 2 columns, the group ID and point number, they can be assigned arbitrarily. So let's say that we have group 1, point number 1, which is uh, so point number 1, and the next 3 columns, they are x, y, and z coordinate of each point. So the first point is this one, so x coordinate of this point is 0.5, y coordinate of this point is 0, and z coordinate is also 0. Then we have the second point, which is under the second support. It has x coordinate at 1, y coordinate at 0, z coordinate at 0. Similarly, we have the third point, which is here at the top. It has the x coordinate at 0.5, y coordinate at 0.5 and 0. Similarly, the fourth point, 0.5. So this is at 1, 0.5, and 0. And similarly, the other points. So after adding all of these points in Notepad like this, so this is the group ID first column, the second is the point number, this is X coordinate, Y coordinate, and Z coordinate. I will save this file with some short name, maybe the tower. Let's keep this tower. And then I will open ANSYS design modular. And in this design modular, I can see that we have this point option that is available. So after clicking on this, we can set the base plane to XY and coordinate units that are added in this file. So they are in meters. So the coordinate units, they are in meters. And I can simply select the file and click on this generate button. So after clicking on this generate button, you can see that all of these points, they are automatically generated from the file. Now I can simply uh, use maybe this XY plane like this one. So I can simply go to the concept and create the lines from points. And in order to add the lines, I see the connections here. So they are zigzag. So this is the first line, then this is the second line, this is the third line, this is the fourth line. So we have all of these squares like this, and these points are all connected. And after that, we can add the trusses that are added in a zigzag manner like this. So this is the first, this is the second, this is the third, fourth, fifth, and we can repeat this process for these line as well. So this is this simple. So we have the line bodies here. I can generate. So here we have a single line body that is added in the answers. And I can add the cross section. So it is possible that a tower or a crane, it can consist of multiple cross sections. For that scenario, you have to create multiple line bodies individually by generating the lines. So in the scenario that I have here, so the cross section is 3 by 3 millimeter rectangular bar. So this is available in ANSYS. I can go select the rectangle. So this is 3 millimeter by 3 millimeter. I'll change the units here. So like this. And since this is scarce, so I do not need to worry about the orientation. And I can assign this rectangle and view the results. Like this, I can focus on any of the joint. Here we have the square cross section of for this complete crane. Now I can move on to the model, and in the model the first step is to assign the material, which is structural steel. We can generate the mesh and apply the boundary conditions that are support reactions that are fixed support at the bottom here, and 6 kilonewton force is being applied from the top, or we can also add pin supports here as well, two pin supports. So let's change this and add the uh, force first at the vertex, and the force is acting in negative y direction. The units and its magnitude is 6 kilonewton. So this is minus 6 kilonewton. We have the fixed support. So I'll solve this using both boundary conditions, first with the fixed support and then with the pin support, and let's see what's the difference. I need to find the total deformation, and using the beam tool we can look at the stresses. We can solve this by hitting the solve button. So the direct stress, the maximum stress in this case is 2.03. Actually, the maximum stress is 2.82, and it is occurring here in this bar. So if I can focus on this bar here, so this is the compressive stress that is acting minus 2.82, and I can also look at beam results for other details. Let's look at the axial force. So we can see the force in every member that we have. So in this member, we have the maximum compressive force, which is minus 25.45 newtons. Let's change the support type here. I will suppress this to the simply supported support. So the simply supported support, we have restrictions on displacement. So the displacement at these 2 points, it will be 0 in x, y, and z direction, and the rotation is allowed in the z direction for a pin support at these points. And when we solve the problem for this, we have the total deformation axial force to be minus 25 Newton as maximum, and the stresses and deformations here in this one. So this way we can use these two different methods for modeling the line elements for complex shape. Finally, you have this assignment for you, which is a three-dimensional truss, and the coordinate points are mentioned here, and there are multiple design loads that are acting at different locations, and the cross section is L-shaped cross sections. So try to solve this one. Best of luck for this, and thank you so much for listening. I will be back with the next lab soon.